All right, let's jump straight into this explainer. Today, we're unpacking one of the most unstoppable forces on our planet, the terrifying, raw physics of tsunamis. We're going to break down exactly how these devastating forces actually work.
To really grasp this, you have to picture the open ocean. Out there, a tsunami can race across the water at the speed of a jetliner. We're talking up to 1,000 kilometers per hour. It's an absolutely unimaginable transfer of energy, just moving silently beneath the surface.
And when all that energy finally strikes the shore, the devastation is just staggering. Take the 2011 magnitude 9.0 earthquake in Japan, for example. That single resulting wave left over 18,000 people dead or missing, completely overwhelming massive infrastructure in its path.
And the sheer height these waves can reach? It practically defies logic. 900 meters. Back in 1958, an Alaskan earthquake triggered a massive 81 million-ton rock and ice fall into Lituya Bay. It created a localized wave so colossal it reached 900 meters high, literally scouring a mountainside clean.
Okay, Section 1. The Unstoppable Ocean Force. Let's look at what actually bursts these monsters.
If you take a look at this breakdown, you'll see that nearly 3/4, 72.3% to be exact, of all tsunamis are violently birthed by massive underwater earthquakes. So while landslides and volcanoes play a part, seismic activity is by far our primary trigger.
Moving right along to Section 2, Anatomy of a Tsunami. What is happening deep beneath the waves?
Think of it like a giant spring. An oceanic plate slowly slides under a continental plate, and immense stress builds up over decades or centuries. Eventually, the overriding plate just snaps. This violent tectonic snap vertically displaces the seafloor, which in turn violently shoves a massive column of seawater upward.
Gravity instantly pulls that massive column of water back down, sending ripples out across the deep ocean. The crazy thing is, out there, they're barely noticeable, small swells. But as they hit shallow coastal waters, friction compresses all that energy, transforming those tiny swells into towering 40-meter walls of water.
This brings us to Section 3, the Ring of Fire, the most dangerous neighborhood on Earth.
This horseshoe-shaped zone stretches an absolutely massive 40,000 kilometers around the Pacific Basin. It's wild because it hosts up to 90% of the world's earthquakes. It is essentially a continuous fault line just waiting to snap.
And this illustrates just how interconnected we all are. An 8.7 to 8.8 magnitude snap all the way in Russia's Kamchatka Peninsula triggered 4-meter local waves. But the ripple effects? They sent advisories to the U.S. West Coast and even set off sirens and suspended flights all the way in Hawaii.
All right, Section 4, from swell to monster. Let's look at the physics of how it actually strikes the shore.
Scientists call this process run-up. It dictates exactly how high and how far the water is going to surge inland. It's an incredibly complex hydrodynamic transformation driven by dispersion, nonlinearity, and the friction of the ocean floor itself.
To even attempt to predict this run-up, researchers have to rely on some seriously advanced hydrodynamic modeling and shallow water equations. They're factoring in everything from the exact depth profile of the ocean floor to the literal rotation of the Earth.
And through this modeling, they've found the absolute worst-case scenario, an N wave. Specifically, this is a wave where the water eerily retreats from the shore first. When you see the ocean draining away, it's basically the ocean winding up for a maximum impact punch on coastal structures.
Which leads us to our final part, Section 5, Racing Against the Wave. How do we outrun this? Well, our very first line of defense is the DART system. This is a network of deep ocean hydrostatic pressure sensors sitting on the seafloor. As the wave passes overhead, they detect the pressure change and instantly beam an alert via satellite to surface buoys and warning centers.
But man, it is not easy. Take a look at this spectrogram. The biggest challenge scientists face is that the tsunami's pressure signal is heavily hidden, just masked by all the chaotic seismic and hydroacoustic noise of the earthquake itself. Finding it requires incredibly rapid processing.
Honestly, the only reason these warning systems even work is because we have a physics loophole on our side. You see, seismic data travels through the solid Earth at up to 13 kilometers per second. That is way, way faster than the physical water wave, which only travels at a fraction of that speed. This critical speed difference creates a window of time for what we call teletsunamis, global waves. Think back to the 2004 Indian Ocean disaster.
The massive quake in Indonesia meant the tsunami traveled silently across the ocean for hours before finally striking the distant coast of Africa. Time really is our only advantage.
So, what does this all mean for us? Ultimately, the next megathrust snap in the Ring of Fire isn't a matter of if, it's a matter of when. The real question is, will your coast be ready, and will you know exactly what to do when the ocean suddenly retreats? Stay curious, and I'll see you in the next explainer.